right, good morning, good afternoon, good evening, depending on when you're watching this. I hope you're going to have a good 4th of July or had a good 4th of July, or maybe you're having a good 4th of July watching this video. I wouldn't bet on that though. So today's first video, this would be the first, this would be kind of the online program for Wednesday. And then of course there'll be another page for us to go through that we'll have to complete before class, okay? But where we left off last time with class, we kind of said, hey, don't forget about these list of probability results. These will still come into play in this new chapter. And of course here we talked about independence and this multiplication rule. But today we're going to continue our talk into modeling random events with normal and binomial models. So last time we met in class on Tuesday, we talked about modeling the phenomenon with these probability distribution functions. And so essentially what they just allow us to do is to model a phenomenon and to be able to more or less summarize this random occurrence, this random experiment that we're observing. So, we got into the craps example, and so there we had the outcomes of a dice, which we said, okay, well, here are the outcomes where I win $1, here are the outcomes where I lose $1, here's the outcomes where I break even, and here's the chances of each. Okay, so these models are really useful in modeling real-world phenomenon and in allowing us to make decisions and to predict the most likely outcomes and to have better gambling strategies in the casino. Okay, but we jumped into the most famous continuous variables. Remember, there's discrete and continuous variables. Usually for discrete we're counting, whereas for continuous we're measuring. So we're going to continue where we left off with the normal model. So just as a reminder, this normal model is a continuous numeric variable, and the normal curve is called the normal curve, normal distribution, or Gaussian distribution. And one thing to note about this curve, unlike the one for the MTD bus waiting time, it's not a constant function. The distribution is symmetric and unimodal. Sometimes they call it bell-shaped. And the notation for this normal distribution are n mu sigma. So this is the Greek letter mu, this is the Greek letter sigma, lowercase. So this is saying, n is saying that it's a normal distribution, and mu is the mean, and sigma is the standard deviation. So we've seen these words before, mean and standard deviation, as measures of center and measure of expected difference from the mean within the other value. Okay, but these before, they came from data. Okay, they came from data, and we call this like x bar, and we call this s. But now we're calling them mu and sigma. So these things are pretty much what we call parameters. Okay, they're not really coming from data. They're things that are already well established, or just some numerical values that are just given to us. Okay, but here, as far as the normal distribution, we just say, okay, for all these different means, the normal distribution is symmetric about the mean. I mean, if I were to cut it in half here, right at the mean, I would get mirror images on this half and this half for each normal distribution. And one thing to note here is that as we go from blue to red to orange, we are increasing the standard deviation. So we're seeing a lot more spread around the center here. Okay. So, and then once again, as far as previously, when we used the empirical rule, we're saying, well, the 68, 95, 99% for the empirical rule. And the empirical rule we can only use if the shape of the histogram was unimodal, symmetric, and no outliers. So pretty much in that rule, what they're doing is saying if your distribution of data appears to be normal, that's what they're saying. Meaning like, okay, this histogram of data, if I do a histogram, it looks like I have some kind of distribution going on here. What can I model this distribution with? But just by looking at the histogram. So what it's saying is that the data is telling us is that by the shape of the histogram being unimodal and symmetric, no outliers, that these observations that we see could be coming from a normal distribution. Okay, so the normal distribution is the reason for the 68, 95, 99.7 rule. And so it follows the same rules as before. The center is the mean, and what we're adding and subtracting to these quantities is just multiples of the standard deviation. So this is 50 to 30, that's within 1 standard deviation. 60 to 10, that's within 2 standard deviations, right? So that's 2 times 10, that's 20. And then of course 70 to 10, that's within 3 standard deviations. So what this says here is this is how we find these areas underneath the curve. Okay, so note here, this is not a histogram. Okay, this is a probability curve. And this is how we could break down the areas underneath the curve. Okay, but this is always very helpful in understanding the probabilities that we get from continuous normal model. Okay, so always look to draw this bell curve and these ticks here, okay, using the 68, 95, 99 rule. So last time we talked about this example about airplane takeoff and other variables, and we talked about BMI. And so what I was doing for you is I was finding all these different probabilities using using properties of the normal distribution. And then of course at the very end I went into StatCrunch and I showed you how to find areas underneath the curve using StatCrunch here. Okay, so if you want to show that one more time, I could show you really quickly how we would do that. So if I could open StatCrunch here and I go to let's see, stat, and I go to calculators. So I go stat, calculators, and I go to normal. Okay, so here I put my mean. So here I could put my mean here. I'm going to enlarge this for us so we can all see it. Okay, so as far as here, the mean I could put 25. Standard deviation I could put 3. I want probability. So here you could do greater than or equal to, less than or equal to. That's what those mean. Okay, so I want to do less than or equal to 20.5. So I do 20.5. And then I compute, and boom, there you go. Okay, so here, what's really neat about StatCrunch is that it'll give you this picture every time, right? So you can see that the area underneath this curve from here to here, right? So if it's to the left of the number that's less than or equal to, okay, the area is roughly, 0.06, 6.7% if we were to round it there, 7% chance, right? So if you randomly select someone, what's the chances that their BMI is less than 20.5? Roughly a 6.7% chance, okay? Now, if for some reason I wanted to do greater than or equal to, what's the probability that it will be greater than or equal to 20.5? Well, we could do complement, right? Or you can click here and do greater than or equal to, and that's what you get there. So see, it shades everything to the right. And in this case, we get 0.993. Okay, but we could do complement 1 minus the previous one to get that result. Okay, and if you ever want to do in between two numbers, well then you probably hit this button here between. See, I can add these ticks there if I want to. So when I push this button here, it'll give me the 68, 95, 99 quantities here. And if I ever want to do between, I can do that. I can say, well, if I do a body mass index between, let's say 27 and 33. Okay, what the heck? We'll do that. So we do that. So there it is here. So here's 27 all the way to 33. Okay, so we want to find the area underneath there. And it gives us this 0.24. Okay. So what I'm going to do today, so that's how we do that in StatCrunch. So what I'm going to do today is pick up where we left off here, and I want to do this. Okay, so now we'll get into a way to find the probabilities using what they call a standard normal table. Okay, so I mean, ideally we're using technology. We're using StatCrunch, Excel to find these probabilities. But using the table is still common practice. I mean, especially within academia, because not everybody's going to have a computer when I test them and things like that. So we may have to rely on the table. And really, using the table, it's not like a setback, because we're going to revisit something called the z-score, and the z-score is still a very important quantity here to interpret, because we've seen these z-scores before, but in the past, instead of mu we had x bar, instead of sigma we had s. But from this quantity, we can really, for a single observation, we can say, well, is this observation unusually far away from the mean or not, right? So typically values that were larger than 3 or smaller than -3, right? Those quantities were associated with being like weird, okay? But anyway, so here in this probabilities table, saying probability of x being less than or equal to 27 is the same as probability of z being less than or equal to z, where z is equal to the z-score. So 27, subtract the mean, divide by standard deviation. So if we're doing BMI here, we're saying that this is 25 and this is 3, and then we get 2/3 here, right? So if I were to what they're saying here, so pretty much what we're doing here is that we're going from this model to the standard model. Okay, we're going to more or less the real life scale to the standardized scale. So just think about typical scale models here, and what they're saying is that these areas underneath the curve, they're both 1, and this area being less than or equal to 27, that's going to be the same as, right, so this area here less than or equal to 27, okay, and this stuff right here, okay, this area here, that's going to be the same as if we were to do the area of z being less than or equal to 2/3, right? So these two shaded regions here, they're saying would be the same. So 2/3 is roughly about right here, right? So this shaded region would roughly be the same. Okay, so the reason we do this is because on your table, these are called the standard normal. Okay, so notice this normal distribution here, it's centered around 0 with standard deviation 1, and so your table is called a standard normal table. So if you ever see the word standard come before normal, what it's telling you is that the mean is 0 and the standard deviation is 1. Okay, so if you want to find standard normal probabilities in StatCrunch, if you check, by default it already has 0 for the mean and 1 for the standard deviation. So by default, StatCrunch has already given you the standard normal model, but of course in there we can change the parameters here. And in terms of math goes, what we're doing from here to here via the z-score, it's a variable transformation. Okay, so we're just doing a variable transformation to help us find the area underneath the curve. So, and then of course here, the z-score, what does it tell you, right? It tells us how far 27 is from the mean with respect to standard deviations. So this positive 2/3 says that a BMI of 27 is 2/3 greater than the average BMI of 25. Okay, but let's go in and see how this works. So how did I get this probability here, right? So once I find my z-score, I'm going to use my table to find this shaded region now, okay, to find this area here. Okay, so if I go to my table, one thing to notice with the table is that this column here, it gives you the ones and the tenths value of the z-score. So it goes from 0.0, 0.1, 0.2, all the way down. Whereas the row, it gives you the hundredths value of the z-score. So it gives you 0, 100, 200s, 300s, and 400s. Okay, so my z-score was 2/3, and if you were to do 2 divided by 3, you get 0.666666666 all the way on forever. Okay, but the z-score, they round to the second decimal place. So if I were to round this number to the second decimal place, I would get 0.67. Okay, so here I get 0.0, 0.1, I get 0.6. Okay, 0.6, so I need 0.67. So I need 700ths, and that would be right here. Okay, so pretty much I go down this column of 700ths until I hit the row that has 0.6. Okay, so pretty much what I'm doing here is battleship. Okay, I find 0.67, and this number here is a probability, or the area to the left. Okay, so the probability that a BMI is less than 27, that's the same as a standard normal being less than or equal to 2/3. And that probability is equal to 0.7486, which gives us 74.86%. Okay. So just in terms of using these tables, all these numbers in here represent probabilities. right? All these numbers in here represent probabilities. They're all decimals between 0 and 1. And the columns here give us the ones and tenths value of the z-score. And this row here gives us the hundredths value of the z-score. So one thing to note, this says table of standard normal probabilities. So what that means is that the mean is 0 and the standard deviation is 1 for the normal. And what it's telling you is that for any given z-score, okay, whether it's negative or positive, it's going to be giving you the less than area, or less than or equal to area. Okay, so that's the only way. So what if I want to find the probability of being greater than, right? What if I want the greater than area? Well, by complement, right? Because the area underneath this curve is equal to 1, right? So by complement, I could just do 1 minus whatever I find here, right? Right, if I want to find the area above, I have to do 1 minus. But just take note that these tables, they give you less than. And if you're Googling around finding different tables, you get different, sometimes they give you different things, but here it gives you less than, okay? So as far as dealing with the standard normal table, you're saying, okay, well, it's giving me only less than, but in practice I may want to find a greater than or equal to probability, or just an in between. And we know how to do that in StatCrunch. It's just a matter of pushing a couple buttons. But what I give you is a standard normal table cheat sheet. Okay, so if the probability is already less than or less than equal to, you just use whatever you find for the z-score is good. Okay, but if you have a probability that's greater than or equal to, well, then we need to do whatever we find from our z table, we have to do 1 minus that, and that's just by complement. Okay, and if you want to do an in between, right, probably x being in between, well, we find the z-score for b, we find the z-score for a, and whatever probability we find for b, we take the probability of a and subtract that away from b. Okay, that's what we do there. Okay, so let's see an example here. So once again, if I were looking at this example here, here we drew, and during class we drew the picture, right? We drew a line here, we shaded this region and found that this region was 50%. Okay, but if I had to go in and find me a z-score here, okay, if I had to go in and find a z-score, okay, so here I say my z-score is equal to, my z-score is equal to, okay, my z-score is equal to, okay, this would be 25 minus the mean, which is 25, divided by standard deviation, which is 3. I would get 0 over 3, and that would give me 0. Okay, so in this case, my z-score is 0, and I can write 0.00 because I know all the z-scores in the table, they give me the ones, the tenths, and the hundredths, just so it makes more sense. Okay, so let's go look up my my z-score, and here it's already in terms of less than. Okay, I know it's already in terms of less than, so I know that I don't have to do any 1 minus or any other tricks when using the table. So here I find 0.00 and I get this area here, which is 0.50, which is 50%, which is what we got last time. Okay, using just by drawing the picture. Okay, so the next example, what I want to do is I want to find the probability that the BMI of a randomly selected individual will be greater than 22. Okay, so in this case, x is greater than 22. So in terms of this area that we're looking at here, right, it's going to give us a shaded region that's like this, right, greater than. So greater than is all the values greater than 22, and then you want to find the area underneath the curve over that interval. So it's everything in here. Everything in there. Oop. Everything in there. Okay, so you want to find all of that, but we know from the table is that if when I look it up in the table, it's going to give me this shaded region here that I didn't color. Okay, so in order to get that back, I just have to do 1 minus whatever I find. So that's all I'm saying here is that let's find our z-score. Okay, we do 22 minus the mean divided by standard deviation, and make sure that this order is correct. Okay, we're always subtracting the mean. Okay, if you did the mean minus 22, you would get a different result. Okay, but it's always subtract the mean away. Okay, so what we get here is -1. So remember, what does this mean? That means a BMI of 22 is 1 standard deviation below the average BMI of 25. Okay. Okay, but anyways, so this value here, I look it up in the Z table, I get 0.1587, and then I just subtract it away from 1, and that will give me the probability of being greater than, which would be 0.8413 or 84.13%. Okay, so I mean, as far as using the table, that's what I did here. This is negative 0.0, and then zeros here. I would get 0.1587. So pretty much what we're saying is that if it's greater than whatever number you get here, just do 1 minus this, and that will be your probability. Okay, so that's what we're saying there. Okay. So just to see an example here, what we're going to do is here, of course, we want to find the probability that the BMI of a randomly selected individual will be between 19 and 40. And so in here, we have one of these between probabilities. And so in using the table, we want to find the probability of x less than 40 minus the probability of x less than 19, and that will give us this area in here. And just to give you a visual as far as how that works is, if we look here, well, 40 is like right here somewhere. Oh, okay, I took my... Okay, so 40 is pretty much out here, so less than 40 is going to be, you know, more or less all of this, right? Less than 40. Less than 40. Okay, so pretty much just the entire curve, if you're thinking about less than 40, right? Alright, so this probability should be like pretty close to 1. Pretty close to 1. And remember, we want to find the probability of it being between... we want to find the probability of being between 19 and 40. So if you see here, we counted too much, right? We counted too much because we needed to stop there, and we didn't. So we counted everything here. I mean, this is the area from 19 to 40. We need all of this, but see this tail here, I counted too much. So this tail, that's what we're subtracting off up here. Okay, this is probability of x less than 19. All right, so probability of x less than 19, it looks like this. Okay, okay, it's all of this in here. Okay, it's all of this in here. X less than 19, it's all of this in here. Okay, so what that looks like is like that right there. Okay. So just to give you an idea, so that's why we write it that way, okay? We pretty much, we take the larger value, find the z-score, and that's our probability, but we would have counted too much, okay? So we need to subtract off this little tail end, and so that's why we do the smaller one, find the z-score, and then subtract away what we find from the table there. So just remember these z-scores here, it's saying -2 is saying that a BMI of 19 is 2 standard deviations below the mean of 25. And then 5 here is saying that, well, a BMI of 40 is 5 standard deviations greater than the average BMI of 25. And in terms of standard deviations, this is a very, very large quantity here, okay? Really, values that are greater than 3, less than -3 are very, very far away in terms of standard deviations. So this 5 is very, very large, okay? And if you're looking up for the z-score, you will not find 5. Okay, so now I look up in my table the z-score for 5, the probability for the z-score of 5, and the probability of z-score -2. And what I'll find is that respectively it's going to be 1 minus 0.0228, which would give me 0.9772, or a 97.72% chance that if I randomly select someone, their BMI will be between 19 and 40. Okay, so just visually here, the largest z-score there is on this table is 3.49. Okay, and the area below it is roughly 0.9998. Okay, so because we're getting further than 3 standard deviations away from the mean, so stuff is becoming less and less likely. So that's why they don't include 5 here. So if you include 5 here, well, if it's less than, then we're going to assume it's 1 because you're going to get the area underneath the entire curve. If it's greater than 5, then we'll get 0 because there's no curve there to find area. Okay, but that's what happens here is that the largest number for the z-score is 3.49, and that's for a reason because values beyond that are pretty much impossible. Okay, so that's why that number was rounded to 1. Okay, and then of course here the z-score of negative 2.0, I get negative 2.00, I get 0.0228, and that's how I found that probability there. Okay, the last thing that we'll talk about in this section is finding percentiles. Okay, and so what we're going to do here in this example is just learn how to find these percentiles of this distribution, but we'll visit this on the next video.